Hello friends and my dear students, I welcome you all to my channel. This video is part of the playlist NCERT Mathematics 9 where I upload videos on the Mathematics 9 chapters of the NCERT textbook, and I uh, right now I am doing the chapter 1 number systems. This is lecture 2. If you have not seen the lecture 1, I recommend that you please see the lecture 1 and then see this video on lecture 2. In this lecture 2 video, we will study about the irrational numbers and we'll try to solve the exercise problems. So let's get started. Okay, so I have opened the PDF of the NCERT textbook, chapter 1 number systems, and so on the left hand side you can see the PDF. We will be discussing in this video the section 1.2 on irrational numbers. I will try to follow line by line the textbook, but I will skip the historic part, like who discovered which formula. All those things I will not discuss. So, in just to give you a brief summary, what we have learned in the previous lecture 1 is we discussed about the natural numbers, the whole numbers, the integers, and the rational numbers. So, we have learned that uh, the rational numbers are the natural numbers, whole numbers, integers, along with all the numbers that can be written in the form p by q, where p and q are integers, q not equals to 0, together forms the collection of the rational numbers. We have also seen how to represent a rational number on the number line. And finally, we have discussed how to find rational number between two given rational numbers R and S, where R is less than S. So we have seen that the rational number R plus S by 2 is a rational number that lies between R and S. Also, we have seen that every rational number can be uniquely located on the number line, and there are infinite number of rational numbers between any two given rational numbers R and S. This also implies that there are infinite number of rational numbers on the number line. Now let's start the irrational numbers. So uh, the textbook says that in the previous section, uh, uh, there may be some numbers on the number line that are not rationals, which means that there could be some numbers on the number line which are not in the form of p by q, where p and q are integers and q not equals to 0. So then what are those numbers which are not in the form of p by q and still they lie on the number line? So these numbers are called irrational numbers. So the definition of the irrational numbers: irrational numbers says that any number s that cannot be written that cannot be written in the form of p by q, where p and q are integers and q not equals to 0. So this is the formal definition of an irrational number. So a number that cannot be written in the form of p by q, where p and q are integers and q not equals to 0, all those numbers on the number line are known as irrational numbers. So let's proceed with the textbook. Now it says that uh, there are infinite number infinite uh, number of irrational numbers. It says that you already know that we already know that there are infinite number of rational numbers on the number line. So it is also true. It has also been found that there are infinite number of irrational numbers. So this is a point to be noted. And some of the example irrational numbers are like root 2, root 3, root 5, right, 5. You have come across these numbers in your previous classes. Also, you possibly also have heard the term pi, whose value is something like it's a it's a long mm, let me see. Yeah, so this is the value 3.14159. It's a long number, and also this kind of numbers where after the decimal point we see infinite number of digits with no pattern, the random number of digits, infinite number of random digits like this. These are some examples of irrational numbers. Now, in the remark, it says that when we say root 2, we mean the positive root 2, because you might be knowing that square root of 4, is 2 as well as minus 2. But when we say here that root 2, root 3, root 5 are irrational numbers, we mean the positive square root. This has to be kept in mind. So now, so you can see the textbook says also root 7, root 10, root 11, root 12 like this. These are all irrational. These are all irrational numbers because they cannot be represented in the form p by q, where p and q are integers and q not equals to 0. Now, to prove that these numbers like root 2, root 3, root 5 are irrational, this you will learn in class 10, not in this class. Okay. So it says that let us return to the question raised at the end of the previous section. Remember the bag of rational numbers. If we now put all irrational numbers into the bag, will there be any number left on the number line? So it says that, so in the number line we have rational numbers and irrational numbers. So the rational numbers are like the numbers in the form p by q. So the rational numbers includes the whole numbers, natural numbers, integers, and all those numbers in the form p by q. Now, if we consider the rational numbers and the irrational numbers, are there any other kind of numbers left on the number line? The answer is no. So the number line, so uh, the number line only contains either a rational or an irrational number. So any point any point you take on the number line, that will be either a rational number or an irrational number. Also, any number which is a rational or irrational can be uniquely located on the number line. Now, this collection of the collection of rational and irrational number numbers is it says uh, the collection of rational and irrational numbers is known as the collection of rational and irrational numbers is called real numbers. So, what are real numbers? Real numbers, which is denoted by the letter R. So, R denotes the collection of all real numbers. And what is a real number? A real number is either a rational number or an irrational number. So, now we see that the number line we have studied so far will have either a rational number or an irrational number. So this number line, so the number line is called the real number line. Because why real number line? Because this number line only contains real numbers. What is a real number? A real number is either a rational number or an irrational number. So the next two very important points, which is written in bold in the textbook, you can see that every real number is represented uh, by a unique point on the number line. Okay, so you take any real number which could either be a rational number or an irrational number that can be uniquely located on the number line. Also, uh, every point on the number line, every point on the number line represents a unique real number. These are important 2 points about the real number line and the real numbers. So let's see. Let's proceed with the textbook. So now it discusses how we locate an irrational number on the number line. So representing irrational numbers on number line. Representing irrational numbers on the number line. So it starts with the example 3 says how do we locate the irrational number square root of 2 on number line. So how do we get square root of 2? So from the earlier classes you have learned from the Pythagoras theorem that when we have a right angle triangle OAB where the base and the height are of unit length, then you know that from the Pythagoras theorem OB square equals OA square plus AB square. This equals 1 square plus 1 square. This is 2. Therefore, OB is square root of 2. So length of OB is square root of 2. So this concept has been used to locate the irrational number root 2 on the number line. As you can see on the in the diagram figure 1.7, what it has done is it has drawn the number line. First it has drawn the number line. So we draw the number line with the 2 arrow pointers, meaning that it extends to infinity on both the sides. If we mark the origin point O, this is origin, we take a unit distance, a point, we represent the point 1 with the of unit distance from O as A. So this is point A, this is represents the number 1. Then what we do is we draw a perpendicular on the number line at point A, and the perpendicular should be of unit distance. So we draw a perpendicular. This is the perpendicular BA on the number line at point A of unit length. So this is 1. Also the length of this BA is 1. Also the length of OA is 1. So in the now what we do is we join the points O and B. We join the points O and B. Now we know from the Pythagoras theorem that OB will be square root of 2. The distance of OB will be square root of 2. Now what we do is we take a compass and with O as the center and the radius OB, we make an arc. O as the center and radius is OB, we make an arc, and the arc will intersect the number line at a point P. At a point P, let's say this was A, this was origin O, and this is point P. So this is How do we draw this arc? We take a compass with O as the origin and radius as OB. We draw an arc. So OB will be equal to OP. OB will be equal to OP will be equal to root 2. So OP is root 2. OP is root 2, which means that the point P represents the irrational number root 2 on the number line. I hope it's clear. This is how we locate the irrational number root 2 on the number line. Now, how do we locate root 3? The example 3 says, the example 4 shows how to locate root 3. The method is same. The concept is how do we get root 3? So root 3, we get root 3 as what is root 3? Root 3 is root 3. So first of all, using the Pythagoras theorem, how do we get root 3? How do we get root 3? So if we consider again a right angle triangle, O A B, what we do is we have to take one side root 2 and another side of unit length. If we take a right angle triangle of root 2 where the base is root 2 and the height AB is 1 unit length, then we know from Pythagoras theorem that here OB square equals to OA square AB square. This will be root 2 whole square this will be 2 plus 1, this will be 3. Therefore, we get OB equals to root 3. So, from a right angle triangle with base root 2 and the height 1, we get the hypotenuse as the root 3. Using the same concept, we will try to locate root 3 on the number line. But as you can understand that first we need to locate root 2, which we have already done in the example 3. So what we do is we draw the number line and we mark the origin. This is 0. From the we draw the previous diagram by locating root 2. We have here the point A, this point B. This was perpendicular. BA was perpendicular to the number line, and this OB was root 2. And with OB as the radius and center O, when we draw an arc that intersects the number line at P, so this is 1. This distance O is 1. So the OP now is root 2. So this is now root 2. what we now do is we draw a perpendicular to the line OB, and at B, let's say, of unit length. So we draw a perpendicular DB to the line OB. Perpendicular, we draw a perpendicular DB at B to the line OB, so that DB is of length 1. So this is the right angle triangle again. When we join OD, so this triangle ODB is similar to this triangle OBA root 2 1. So we have OD as root 3. We will have OD root 3 from the Pythagoras theorem. This is the right angle triangle. ODB base is root 2, height, the perpendicular is 1, so the hypotenuse will be root 3. Now what we do is, similarly, we taking OD as the radius and O as center, we draw an arc with the compass, and the arc meets the number line at point Q. So we will have OD equals to OQ, because we are drawing an arc with center O and radius OD. So OD will be equal to OQ. So OQ will be, the point Q will represent now the number root 3. In this way, we can also look at root 4. Even though root 4 is 2, we can straight away mark the point of unit of 2 unit distance from O. We can also look at root 5. How do we look at root 5? So to locate root 5, we need to locate root of 4. You see the pattern. How are we locating a square root of a natural number? To look at root 2, we needed 1 and 1. To locate root 3, we needed root 2 and 1. The 1 of the right angle triangle, 1, the perpendicular, that will always be there. We will always need that 1. Just the base will change. To locate root 3, we needed the base to be root 2. To locate root 5, we will need the base to be root 4. To locate root 7, we will need the base to be root 6. So in this way, we can locate any irrational number of the form root over n, where n is a natural number. Let's see what is there in the, so this we have seen. Now this is a very important concept that is written, that to locate the irrational, not irrational number, because root n may not be an irrational number, like root 4, it is 2. 2 is not an irrational number. So root n is irrational only when n is not a perfect square of another number. So we can say, to look at the irrational number root n, where n is a positive integer and not a perfect square. What do we mean by perfect square? Like, it is not 4, it is not 9, it is not 16, it is not, not 25. So it is not a square of another number. That is what we mean by saying that n is not a perfect square. So n is a positive integer and not a perfect square. In that case, root over n will be an irrational number, and to locate the irrational number root 10, we need to locate root over n minus 1. So we can locate root over n only when we have located root over n minus 1. Now, uh, before doing the exercise 1.2, let me explain uh, a few more examples. How do we locate irrational numbers? So, let's say exercise. Let's say exercise. Locate, let's say, root 5 on number line. So to locate root 5 on the number line, what we need is to locate root 4, and root 4 we already know is 2. So what do? We first draw the number line and we mark the origin O. This is 0. Now what we need is to locate root 5, we need to locate root 4. What is root 4? Root 4 is 2. So 1, 2. Let's say this is point A. So now at point A we draw a perpendicular BA on the number line BA. This is B. Of unit length. BA is of unit length. OA is 2, BA is 1, BA length is 1, OA is 2, AB is 1. We draw perpendicular BA on the number line at point A. Now we join OB. And from the Pythagoras theorem, based on the right angle triangle OBA, we know that OB will be, what will be OB? OB will be OA square plus AB square. OB square will be this. This will be OA square is OA is 2. So 2 square plus 1 square. This will be 4 plus 1. This will be 5. Therefore, OB will be root over 5. The length of OB will be root over 5. And now, with OB as radius and center at O, using a compass, we will draw an arc that will intersect the number line at a point P. And obviously, we will have OB equals to OP, and so OP will now represent the point. So OP will be the length of OP will be root 5. So the point P on the number line will now represent root over 5. So what are the steps? To look at root 5, we need to locate root 4. Root 4 we know it is 2. So we directly mark the point 2, which is A. And then we draw a perpendicular BA at A to the number line, and BA should be of length, unit length 1. We joined OB, and then with OS center and OBS radius, we draw an arc which intersects the number line at point P. From Pythagoras theorem, OB will be root over 5. So OP will also be equal to OB. So OP will be root over 5. So we have located root over 5 on the number line. Let's see how we can locate let's say root over 6. locate root 6 on number line. So to locate root 6 on the number line, we need to first locate root 5. Root 5 we have already located in the previous example. So we have to first locate root 5. Uh, so we have to locate root 5. Let's say we have already located root 5. I am redrawing the diagram for the previous example. So we have, say, A is 2 and we did B, this was B, this was OB was root 5, and we found arc, the point P is root 5. So OP is root 5. Now to locate root 6, what we do is we draw a perpendicular at P on the number line of unit length. Let's say this is C. So CP is a perpendicular on the number line at the point P of unit length. Now if we join OC in the right angle triangle OC OCP, we will have, according to Pythagoras theorem, OC square equals to OP square plus CP square. OP square, OP we have already know, P represents the irrational number root 5. So OP square will be root 5 square plus 1 square, this will be 6. Therefore, OC is root 6. OC is root 6. Again, what we do similarly is taking O as origin and OC as the radius, we take a compass and draw the arc. And this will intersect the number line at point, say, Q. And OC will be equals to OQ. OC will be equals to OQ will be equals to root 6. And therefore, the point Q will represent the rational number root 6. The same concept, using the same concept, you can locate any number root over n. First, we have to look at the root over n minus 1. So, for a given n, if n minus 1 turns out to be a perfect square, then you can straight away locate the point n minus 1 on the number line. Let's say, you are asked to locate root 10 on the number line. So first we have to locate root 9, and root 9 we know is 3. So we directly locate the number 3 on the number line. And at that point we draw a perpendicular of unit length, and we join that point of the perpendicular, the upper point of the perpendicular with the origin, and we draw an arc. And as per Pythagoras theorem, we will have the arc where the meeting point of the arc and the number line will represent root over 10. Just to give you, let's say, locate root 10. Locate root 10 on number line. So what we do, okay, so first first we need to locate root over 10 minus 1 equals to root over 9 equals to 3 on number line. So in this case, we first draw the number line, take the origin 0, mark the point A, so let's say this is 3. We need to first locate root over 9. Root over 9 is 3. So we have located 3. Now what we do is we draw perpendicular at A on the number line of unit length. Let's say this is B, unit length. We join OB, and so OB will be OB square as per Pythagoras theorem, OA square plus AB square. This will be OA square is 3 square plus 1 square. This is 9 plus 1. This is 10. Therefore, OB will be root over 10. OB will be root over 10. And now we will draw an arc with OI center and radius OB, and that arc where the arc meets the number line, intersects the number line, that point P will be equal to OB. I mean OP will be equal to OB, and OB is root 10. So OP will also be root 10. So P point on the number line will represent root 10. So we have located root 10 on the number line. So in this way, for any root over n given, you can locate that number on the number line. I hope these examples will be enough to give you an idea how to locate any irrational number of the form root over n. So let's see try to do the exercise. Number 1, state whether the following statements are true or false. Justify your answers. 1. Every irrational number is a real number. Every irrational number is a real number. This is true, of course, because we have learned that every real number is either an irrational number or an rational number. So obviously, an irrational number is also is also a real number. The reason you can say is that every real number is either a rational or an irrational number. This is a pretty good reason. So every real number is either a rational number or an irrational number. So obviously an irrational number is definitely a real number. Number 2 says every point on the number line is of the form root over m, where m is a natural number. It is saying that every point on the number line. So if we take randomly a point on the number line, it will be of the form root over m, square root of m, where m is a natural number, like root over 2, 3, 4, 5, 6. Now this is false because there are points on the number line which are not of the form square root of m. For example, the rational numbers, the integers, whole numbers, natural numbers, they are also part of the number line. But consider a positive integer 4, where m is a natural. Every point on the number line is of the form root over m, where m is a natural number. Uh, every point on the number line is of the form root over m, where m is a natural number. Every point. Hmm. For irrational numbers, definitely it is. mm, if we take any integer, if we take any integer, whether it's if we take any positive integer, then definitely it can be written in the form of root over m, where m is the natural numbers. In that case, we will have that m's uh, integer. If we take an integer, if we take an integer number x, that can always be written in the form of root over m, where m is a natural number, because we will have then x square is m. You take any integer, positive integer, 2, 3, 4, let's say 5. I can say that 5 is square root of 25, and 25 is a natural number. Now it is saying every point on the number line. So by every point, we can see for integer it is true, for positive integers it is true, for negative integers, mm, negative integers, uh, for negative integers, let's say minus 2, do we have m where minus 2 equals square root of m? That is the question. If I take a negative integer, let's say minus 6 or whatever, minus 5, uh, we can have minus 5 as square root of 25. Uh, square root of 25, but in the textbook it's mentioned here that recall that when we use the in the remark, recall that when we use the symbol square root, we assume that it is the positive square root of the number, positive square root of the number. So root 4 is considering as 2. If we follow this statement, if we consider in mind this remark, this statement that by square root of 4 we mean 2, so definitely the square root of m, it has to be a positive number. So with square root of m, we won't be able to mark a negative integer. And where m is a natural number. Also, what about rational numbers? A rational number is also part of the number line. Can we represent a rational number in the form p by q as root over m? Let's say, I think this is false definitely, but a proper reason is, let's say we have a rational number. This is a rational number. Can we represent this rational number in the form, can we write it equals to in the form root over m, where m is a natural number? I don't think so. So a rational number in the form, or rather a fraction in the form, a rational number in the form p by q, where it is not an integer, a rational number which is not an integer, and in the form p by q, like 1 by 3, or let's say 2 by 6, 3 by 7, like that. These kind of rational numbers cannot be represented in the form of root over m, square root of m, where m is a natural number. So definitely uh, this is false. Reason, since it says that every point on the number line is a form, no, this is not true, because a rational number, a rational number in the form P by Q, where Q not equals to 0, and uh, and we must have uh, and P by Q is not and is not uh, an integer, that is, P by Q is a proper fraction. You have learned fraction in your previous class, so I hope you're familiar with the term fraction. So, in a rational number in form and P is not in the, cannot be cannot be uh, of the form root over m, where m is a natural number. So we cannot represent a fraction p by q, where p and q are integers and q not equals to 0, in the form root over m, where m is a natural number. So, and since a fraction or a rational number belongs to the number line, it proves that every point on the number line cannot be of the form root over m. I hope it is clear. Let's see what is number 3. Every real number is an irrational number. No, this is false. Every real number is not an irrational number. The real number, the collection of real numbers, is the collection of rational numbers and irrational number. And so the reason could be that all rational uh, number are real numbers, and they are not irrational numbers. So obviously, a rational number is not an irrational number. We know this, uh, and we know that the collection of the rational numbers, and the irrational numbers together forms the collection of real numbers. So any real number, every real number, it says every real number is a natural number. That is false. Every real number means a real number. It is also saying that a rational number is an irrational number. No, that cannot be. Rational numbers are different from irrational numbers. Meaning, we know that a number which exists on the number line, which is not a rational number, which means it cannot be written in the form p by q, are known as irrational numbers. So definitely this is false. So okay, so what is 2? What is problem number 2? Are the square roots of all positive integers irrational? Are the square roots of all positive integers? By positive integers, we mean the natural numbers like 1, 2, 3, 4, 5, 6, 7, 8, like this. It says, it is asking, are the square roots of all positive integers irrational? No. This is no. No. Reason, If not, give an example of the square root of a number that is a rational number. So, square root of 4 equals 2 is not an is not a that is a rational number. If not, give an example of the square root of a number that is a rational number. It says are the square roots of all positive integers irrational. Okay, so square root of 4 uh, is 2 is a rational number. Is a 2 is a rational number. 2. See, it says it is asking whether the square root of all positive integers are irrational or not. The answer is no. We are giving an example that 4 is a positive integer, and if we take square root of 4, it is 2, and 2 is a irrational 2 is a rational number and not an irrational number. So it proves that the square roots of all positive integers are not irrational. 3. It asks to locate root 5 on the number line. We have already done that, I guess. Yes. You can see this example how we located root 5 on the number line. Now, 4 is a classroom activity. Uh, this activity shows how to construct square root of spiral. So, what it does is that it continuously finds the irrational numbers root 2, root 3, root 4. Even though root 4 is not an irrational number, it is 2. It is finding the square root of n, where n is a natural numbers. Like square root of 1, it is 1. So square root of 2, square root of 3, square root of 4, square root of 5, square root of 6. This way, when we try to find these numbers by using the Pythagoras triangle, we see a spiral, as you can see in the figure. So let me quickly describe what is happening here. We take first a point O, and we take a unit distance OP. We take a point P of unit distance. This is OP is 1, and what we do, we draw a perpendicular. Let's say this point is P1. We draw a perpendicular on to OP1 at point P1 of unit length. Let's say this is P2. We then join OP2, and this is perpendicular. So what? So OP2 will be root 2. So we take a point O, we take another point P1 with OP as unit distance 1. We then draw perpendicular P1 P2 at point P1 on perpendicular to OP1. This P1 P2 is unit distance. This is 1. So by Pythagoras theorem on the triangle OP1 P2, we get OP2 as root 2. What we then do again, with OP2 as base, we draw a perpendicular on OP2 of unit length. Let this be P3. This point is P3. P3 P2 is perpendicular to the line OP2, and this P3 P2 is of unit length. So again, by Pythagoras theorem, uh, by oh shit, undo. Okay, so this is perpendicular. This is perpendicular. So by Pythagoras theorem, we will see OP3 will be root 3. Again, we draw perpendicular to the line OP3 of unit length. Let's say this point P4, P3 is perpendicular to OP3. This is unit length. And we will see now how come this is root 3, because this is 1 and this is root 2. So 1 and root 2, Pythagoras theorem, this hypotenuse will be root 3. Similarly, over here, if we join P4, OP in this right angle triangle, this is root 3, OP3 is root 3, P4, P1 is 1. So this hypotenuse OP4 will be root 4. This way, again, if we draw a perpendicular to OP4 of unit length, let's say this is P5, this is 1, and we this is perpendicular, and we draw so this OP5 will be root 5. Similarly, again, if you draw perpendicular to OP5, perpendicular of unit length, let's say this point is P6. P6, P5 is perpendicular to OP5, and this is of unit length, and we join P6O. This will be, this hypotenuse OP6 will be root 6. So this is what is known as constructing square root spiral. As you can see, it is forming a spiral this way, this way. So we will have like this. It will go on, and we will find the all the hypotenuse will be then root 7, root 8, root 9, like this. This is classroom activity for constructing the square root spiral. In this manner, as it says, in this manner you will see, so in this manner you will see, have created the points P2, P3, etc., Pn, and joined them to create a beautiful spiral depicting root 2, root 3, root 4. So the points P1, P1, P2, P3, P4, P5, P6, if we join these points, we will get a spiral. And in this way, we are we are creating this the creating lengths, these values root 2, root 3, root 4, like this, as it is shown. So that was all for section 1.2 about the irrational numbers. I will end this video here, and in the next video, in the next lecture 3, we will start the section 1.3 on real numbers and their decimal expansions. Now, please note that I will also solve the exemplar problems, but at this point of time, it will make no sense to do the exemplar problems. So it's better where we will complete the whole chapter, then only we will solve all the exemplar problems, if not all, most of them. So stay tuned for the upcoming videos, as I will be following the NCERT textbook almost line by line, explain the solved examples, and we'll also do the exercise 1.2. So yeah, that's it for this video, and I hope you are learning with me, and please, if you are learning something, if you found this video beneficial, then please support me by subscribing to my channel, as I will be continuously uploading videos as while I will study the uh, subsequent chapters. So thanks for watching, and until the next video, take care and bye.